Good morning. We're going to go over more examples involving boundary value problems that lead to Bessel equations. So we're going to focus on applications primarily, and we will revisit actually some of the earlier concepts, but now viewed in this different coordinate system. So remember, the only reason so far we met Bessel equations in our examples is because we use cylindrical coordinates, and that changes essentially the nature of the Sturm-Liouville problem from the one we encountered before that led to sine and cosine series to the Bessel equations that led to Bessel function or Bessel Fourier series. So if you have, I hope you have in front of you the formula sheet, I mean the handout with the summary on Bessel functions. So if you don't, pause for a moment because it's very important to follow with me that handout. So in that handout, you'll notice that there are actually three types of boundary conditions when we gave the formulas for the Fourier-Bessel coefficients. And we had already examples of the, I think the label was A and C. So the first and the third type when you had Dirichlet conditions or Newman conditions. But there was another one with mixed conditions labeled by B in the formula sheet. So namely, it says that, so in that formula sheet, it says that you could have a Fourier-Bessel representation for a function, piecewise continuous, from 1 to infinity, in which, first of all, alpha j are the roots of h times j naught of alpha c plus alpha c times j naught prime of alpha c equals 0. So this is like a mixed type of boundary condition because it contains both j naught and j naught prime. And then the Fourier coefficients, aj, are given by this more complicated format of the coefficient 2 alpha j squared alpha j c squared plus h squared. So you have this large coefficient, large constant on the outside, times j naught of alpha jc quantity squared, and then everything times the integral from 0 to c x f of x j naught of alpha jx dx. So I want to go over the main application that leads to this Fourier-Bessel series, and in particular to this boundary condition. So this is obviously provided without proof because we won't have time to go over the details. You can look in the book if you want, but just like by themselves, j naught or j naught prime have infinitely many roots, one can prove that this combined condition will have infinitely many roots, positive, alpha 1, alpha 2, alpha 3, and so on. Okay, so in this case, j goes from 1, 2, 3 up to infinity. So once again, make sure everybody understands this. The alpha j's come from the boundary condition. So the alpha j's denote the infinitely many positive roots of this condition. And so then you can find the Fourier series representation in terms of these Bessel functions. H is a physical constant as well. So H is greater than 0. And again comes from, because now, as the title mentions here in the presentation, this condition, as I'll show immediately, comes from the Newton law of cooling under certain assumptions. So H is a physical constant related to the Newton's law of cooling. So let's remember what the Newton's law of cooling states from a physical perspective. So if you have an object, in this case, obviously the object is in the cylindrical form, and we assume that the surrounding medium, so the environment in which this object is placed, maintains a constant temperature. So let's say the environment is big enough and the object is small enough so that the outside of the object doesn't really change the temperature, but the environment will influence the temperature of the object. So there is heat transfer from the environment to the surface of the object. The object is modified by the environment temperature, but the temperature on the environment stays the same. So this big T, the exterior temperature, is going to be constant. So in general, for any object, doesn't have to be in the cylindrical form. In general, and this is also given in the book, the Newton law of cooling states that, or heating, because the surface can go up or down depending on the temperature compared to the exterior of the object. So the Newton law of cooling states that the heat exchange, the heat transfer across the surface follows the following law. Some physical constant K, the derivative of U, the temperature with respect to the normal across the surface. I mean, this is the meaning of N here. And it says that this heat transfer is proportional to, this is another constant, proportional to the difference between the exterior temperature and the temperature of the object on the surface. So this is, this law is, in the case of cylindrical coordinates, is when the radius is equal to C. We'll get to that in a moment. But again, this law is regardless of the shape of the object. This is a directional derivative. Directional derivative in the direction of the heat transfer, which is basically the direction of the gradient, space gradient. Now, in the case of cylindrical coordinates, under our assumption, our simplifying assumption that the heat really flows across the radius, right? I mean, the heat flows from left and right, basically. Then the direction of the radius is going to be the directional derivative in which the heat flows. So it will be simply the partial derivative with respect to rho, right? The variable that denotes the radius in cylindrical coordinates. So let's see how this law looks like, again, in cylindrical coordinates. In which the space coordinate is given by rho. And let's say the rho is between 0 and C, as we normally denote the domain, right? C is the exterior radius, right? So this is C, the outer radius of the cylinder. So in cylindrical coordinates, rho is between 0 and C. And let's say also, in addition to that, an extra assumption, let's say the exterior temperature is equal to 0. So then this law, look carefully now, this law, the Newton's law of cooling, now looks at the following way. Some constant K, partial rho, evaluated at C and T. Okay, so let's say U depends on just on the radius and the time T. Again, at C, not at rho in general, because this law of cooling is essentially a heat exchange transfer on the surface. So the exterior influences the temperature of the surface. And then on the right-hand side, if the exterior temperature is 0, we're going to have minus some other constant h, u of Ct. So that becomes a boundary condition of mixed type, right? So you have both the value of u at the boundary point and the partial derivative with respect to the same boundary point. With that in mind, let's change a little bit this for convenience. Let's combine these constants a little bit. So let's divide by k. So you have u partial rho of Ct equals minus h over k u of Ct. And just for convenience, let's multiply both sides by c. Remember, c is a constant. It'll make essentially the boundary condition given in the formula in a more compact way. So c again is a constant. We can multiply both sides. So then the left side now looks like c u partial rho at Ct equals minus big H little c over big K u of Ct. And to achieve, to get in the end to that boundary condition in terms of the Bessel functions, let's denote or rename this physical constant, or this combination of physical constants, by little h. So big H times C over K equals little h. So remember, big H is like the coefficient that basically describes how fast is the heat transfer across the surface, and some other physical constants lumped into this new constant little h. So again, this h will be assumed to be known. Either you will have a, oops, it's out of range. Either you will have a given value for it, or it will be specified. It will be just left, generically speaking, as h, right? But you treat it as a known constant. And then if we move all the terms on the left side, then the boundary conditions coming from the heat, Newton's law of cooling, is going to look like this: C u partial rho of Ct plus h u of Ct equals 0. Once again, this is basically the Newton's law of cooling assuming 0 exterior temperature, and in cylindrical coordinates assuming further that the heat flows just in the direction of the radius, which is the reason you have u partial rho here. Okay, what this has to do with the Bessel functions? Well, as you will see in the example that I'm going to solve leading to this type of boundary condition, if you were to proceed with separation of variables, then when you plug in the separated form for u, you're going to end up, because remember now u of rho t will be some function of rho, some function of t. So when you plug this in and simplify, you're going to end up with the following condition on R. So C R prime of C plus H R of C equals 0. So remember, previously, in the previous cases, we had R of C equals 0 now, or we had R prime of C equals 0. Now we have a combination of these, and this will be the condition. And if, as we expect already, if R of rho comes from the Bessel equation, then we know that its solution will be, if it's a Bessel equation of order 0, will be J naught of alpha C. So then if we plug in J naught of alpha C into this condition, then we're going to end up with the following boundary condition for the Sturm-Liouville problem. So C J naught prime of alpha C, but by the way, once we differentiate this with respect to C, we're going to have another alpha on the outside of the function, the chain rule, right? So when I differentiate J naught, it's going to J naught prime of whatever is inside. I should say here, so R of rho, J naught of, let's see, J naught of alpha C, alpha rho, I'm sorry. Yeah, J naught of alpha rho. And then you're going to plug in C, the boundary point, and then differentiate the chain rule, right? If I differentiate with respect to rho, I'm going to have another alpha popping out, which appears over here. And then you have alpha C, J naught prime of alpha C, and then H, J naught of alpha C. So you'll see how this comes out when we move on with the actual example. But this is basically this condition when you plug in this function for R and then apply the, replace rho with C to get the boundary condition. So this is essentially the Newton law of cooling, or the condition coming from the Newton law of cooling, assuming 0 exterior temperature. Okay, so with that in mind, let's move on with the second part when we go over an example involving this type of condition. So stay tuned.